Everyone. So today we'll be discussing about the correction which Planck made in the concept of classical theory of thermal radiation. Unlike classical theory, which considered only that the energy states are not discrete, Max Planck considered that the energy states are discrete and energy of a particle is given as h nu, where nu is the frequency of the particle and h is the Planck constant. Before further progressing, we need to know few concepts. We need to know these three concepts before going further. That is, first is that if you have some particles and you need to find a probability that the particle possesses an energy of E, then the probability that a particle among the given number of particles possess a energy of E, or if you even consider it like the number of particles between E to E plus dE, then it would be some constant k into e to the power minus E by kBt into dE. So similarly, the number density is given as e to the power minus E by kBt, where E is the energy of the particle. And if you ever, for the second point, if you ever come across electromagnetic radiations, you might have come across that the EM wave stores energy in form of electric and magnetic fields, right? So the energy density is given as half epsilon naught E square, and intensity is just multiplication with C. Here the progression is in the same direction. All the wave or the actually basically all the particles or the waves or the wave packets actually progresses in the same direction. But in this case, where we have considered a 3D box, all the particles does not have velocity in the same direction. All the particles do not have velocity in the same direction. That is why we divide it by some factor 4. Well, I am not going deeply into why there is a factor of 4. Well, it would involve some integration, of course. So just know that there will be a factor of 4. Well, you can assume like half of the particles will go. Suppose here is a partition. Half of the particles will go left hand side, half will go right hand side. Because of this, this will be a contribute a factor of 2. Means basically division will be with a 2 and the factor will be half. Similarly, each particle will be diffused in different directions, so another factor of half will be added here, so it will be 1/4 in total. And as discussed in previous lecture about the classical theory, it is this formula is still applicable. N lambda into d lambda is equal to 8 pi by lambda to the power 4 into d lambda. So this was a very important discussion we need to remember before further progression. Well, in the last video we described about the average energy. So average energy E average was equal to some integral E into N d E, something like that. But in this case we have to basically averagize whole energy in discrete form. So that so suppose a particle have energy h nu, so the probability that it will have the energy h nu, or the amount of particles having energy of h nu, will have fraction of e to a minus h nu by kBt. So this will be the total contribution due to the h nu. Similarly, due to 2 h nu, it will be 2 h nu into e to a minus h nu by kBt. Now there may be some particle with energy 0, so it will be 0 into e to a minus h nu by kBt. But the total number of particles will be e to the power minus 0 by kBt plus e to the power minus h nu by kBt, and so on. It will go till infinite. Now one may ask about the pairing, that is according to Pauli's inclusion principle. So there may be two states. Well, I am not going into the two states as the number of particles is very large. So the end correction may be neglected and we may assume it to be infinite. Okay. So you will get something like average energy E is equals to kBt into summation 0 to infinity n epsilon e to a minus n epsilon by summation e to a minus n epsilon 0 to infinity, where epsilon is given as h nu by kBt, right? So we have taken first assumption that E is equals to h nu by kBt. Now this is the numerator is a AGP and the denominator is a GP. Well, you know that how to solve a AGP. Here I'm not solving it. I'm just directly writing the result. Well, if you evaluate, you will get average energy is equals to h nu by e to the power h nu by kBt minus 1. So this will be the expression for average energy. Hope you get it. This is equation 1. Now I can write u lambda d lambda is equals to n as a function of lambda d lambda into E average, which will come out to be 8 pi by lambda to the power 4 E average d lambda into E average, which will be h nu by e to the power h nu by kBt. Now we have written everything in terms of lambda. That is why we will substitute nu as c by lambda. So I can say that I lambda as a function of lambda is equals to u lambda into lambda by c by 4, where u lambda is given as the spectral density, which is a okay. So if you further evaluate, we will get 2 pi c by lambda to the power 4, because we already cancelled out 8 pi with 4, we will get 2 pi, and there's a c, so it will be 2 pi c by lambda to the power 4 into d lambda. Well, I'm not talking about d lambda here. So if I consider the I lambda d lambda, we'll get d lambda into h nu by basically hc by lambda into e to the hc by kBt minus 1. Yeah, here will be a lambda in the denominator. Okay, hope you get it. So finally, I'll get I lambda d as a function of lambda, that is the spectral intensity density, will get 2hc square into pi by 8 lambda to the power 5 into e to the power hc by lambda kBt minus 1, right? And if you integrate the intensity, spectral intensity over 0 to infinite wavelengths, you will get result like 2 pi to the power 5 kb to the power 4 by 15 c square h cube into t to the power 4. And if you remember one thing, that Stefan's Boltzmann law, Stefan's radiation law, that sigma T to the power 4 is given as intensity and power is given as sigma A T to the power 4. And here, since we are talking about intensity, we will consider only sigma. So this is the value of sigma. Sigma is equal to 2 pi to the power 5 kb to the power 4 by 15 c square h cube. And this will evaluate out to be 5.67 times 10 to the power 8 minus 8, 1 minute, watt per meter square Kelvin to the power 4, right? Hope you get it. Now, proving the Wien's displacement law, just the same result, we need to consider di by d lambda to be 0, and we'll get some transcendental equation as y e to the power y by e to the power y minus 1 is equal to 5, where y is given as hc by lambda kBt. And you know this is a transcendental equation. We need to find an approximate solution. We cannot get the exact solutions because this equation is wired. So we need to find the intersection with the graphs and all those. You can use this mouse and find the intersection between 1 minus 1 by e to the power y is equals to y by 5. Then you will end up some result as y is equals to 4.965. Pretty interesting. Now, well, you can see even one thing to notice, that as y is greater than, suppose 3 or 4, you can write e to the power y minus 1 is nearly equal to e to the power y. This is an interesting result to note, because already it's too large. Well, this is 3 or 4, not 3 by 4, for your information. So we know that e to the power 3 is greater than 27, is just less than 27, right? And it's greater than, you can say 10 also. So 10 by 9 can be written as 11.11, and even it's actually greater than 10, and 27 by 26 is nearly 1. So e to the power y minus 1 is nearly equal to e to the power y. So we are getting a result of y which is nearly same as 5, because 4.965 can be nearly written as 5. Thus, we will get Hc by lambda kbt is equals to 4.965. Hence, putting the value of Hc and kb, we'll get lambda t is equals to 2.8978 millimeter Kelvin. We just proved out that Planck radiation was so helpful. Planck's theory was so helpful in this that it actually even fit with the graph. Planck's graph actually fitted with this graph. The I as a function of lambda and lambda. So this was a very peak level achievement done by Max Planck. Now Olympiad may ask you that after they will give you the Rayleigh Jeans formula, they will say that this was a failure because they didn't consider the discrete energy levels. Hence, we have to now apply some AGP. They may give you the formula of AGP, or you have to derive in the result in the exam, because we already study AGP in 10 plus 2 standard. Then if we then we'll find the average energy, and we already found u lambda d lambda is equals to n lambda into t lambda into e average. Now substituting the values, they will ask you about the energy density per unit wavelength as a function of wavelength, which will come out to be 8 pi by lambda to the power 4 into h nu by e to the power hc by lambda kbt minus 1. And here I am substituting nu as c by lambda, which will give h 8 pi by lambda to the power 5 into hc by e to the power hc by lambda kbt. Well, it's looking like it's in multiplication. Let me modify it a little. Then we know that I lambda is equals to u lambda into c by 4, as we described in the at the first. Then further evaluation will get I as a function of lambda, integrating the I as a function of lambda over the whole wavelength, we will get some intensity. Now olympiad askers or the teachers may give you the ask you the integration of this, will actually provide you some support with some formulas like integral of x cube by e to the power x minus 1. Why? Because 1 by lambda you will substitute as some u, then you will get du is equals to 1 by lambda square d lambda, negative sign. Then just it's lambda cube into lambda square d lambda into e to the power hc by kbt into 1 by lambda minus 1. Putting 1 by lambda as u, you will get integral u cube du by e to the power hc by kbt into u minus 1. So they may give you this equation because these two equations are almost similar to each other. Hence, then you have to find the integral, and you will end up with the result of t to the power 4 in the denominator, in the numerator, and the prefactor has some 2 pi to the power 5 kb to the power 4 upon 15 c square h cube. Finally, we'll end up the value of the prefactor, and at the last they may ask you to prove the Wien's displacement law, and you will get some y e to the power 5 by e to the power 5 y minus 1, and they will tell you to assume that e to the power y is very large if y is greater than 5 or greater than 4, and you will consider the numerator and denominator, you will end up y is equals to 5. Then you will get the Wien's constant also. So I just told you that how all the teachers who sits the paper of IN PHO or USA PHO can approach you. Hope you enjoyed it. Thank you. Have a nice day.